Good day, this is Engineer Mark and today I'll be presenting about implementation strategies for digital ICs. One major observation regarding digital design is that since the last 40 years, there has been a design gap, which means chip complexity grows faster than design productivity. Compound complexity growth, or the number of transistors per chip, increases at 58% per year as predicted by Moore's law. On the other hand, compound productivity growth rate, which can be measured through the number of transistors that a single designer utilizes to construct digital circuits for every month of work, increases at about 21% per year. Due to this design gap, there has been an increase in team size or the number of designers per project, which is inevitable and required to compensate for the difference in growth rate. As said earlier, compound complexity growth rate increases as stated by Moore's law. But what governs the compound productivity growth rate? Productivity increase is because of new design technologies. Shown here are the various design technologies throughout the year since the 1970s. We started from an era in the 70s when the 4004 was designed by hand. Every circuit was designed transistor by transistor. Then in the late 70s, programmable logic arrays were introduced, followed by standard cells, then macro cells, then gate arrays, then reconfigurable hardware. All of these will be discussed later on, but what we need to understand here is that there has been more and more software helping the designer to design complex circuits. Moreover, we can observe an increase in the complexity of the software that helps the reuse of hardware modules. Before going to some more details in what these technologies mean, let us look first at the general components of a complex digital integrated circuit, such as microprocessors and digital signal processors. Here we can see that we have four main blocks. We have the control block, which is connected to a memory and data path. The memory and data path in turn are interconnected to a block, which takes care of the input and output, and to the interconnections with the external world. All of these different blocks have different types of circuit. In the data path, where the combinatorial functions and arithmetic operators are done, in this block, we typically require custom cells, which means digital blocks that are designed on purpose to work on the data path module. The control block is essentially a finite state machine, which is built with standard cells. Standard cells are reusable logic gates and single registers or single blocks of registers that can be used as a standard building block of the combinatorial circuit of a finite state machine, so that each block is designed only once and then used in different types of more complex circuits. Then we have the memory. Memories require very specific types of components. We have various types of memories and we also have various ways to classify them. According to writability, we have read-only memory and readable and writable memory. According to the number of access, we have memories with single port access and memories with multi-port access. According to volatility of the memory, we have dynamic RAMs, static RAMs, and non-volatile memories. For memories, we use regular macrocells, which means typically the building blocks of each type of memory are already designed and they are available to form a larger memory block. Finally, we have the input-output circuits. We need specific components which are buses and interconnects and are typically macrocells. Macrocells mean they are larger component and very specific for this type of application. Since input output circuits communicate to the outside world, silicon chips should have larger drive currents because outside the chip everything is larger. Larger capacitances, larger currents. So the blocks must be able to cope with that type of circuit. So we have here the block diagram of a complex digital integrated circuit, together with the specific types of components that each block contain and require. In addition to the components, the other thing that is extremely important is how these components are interconnected and how are we going to provide a power supply and a clock signal to the different components. And these are difficult tasks to do, and the way we address these problems for the various building blocks depend on the type of block. For example, in the case of memory and in the case of interconnects and input-output circuits, typically we have a very regular structure, so also the interconnections are going to be extremely regular. In addition to that, a specific aspect of the interconnect and input-output block is, from the external world, the power supply and clock signal has to be distributed to all blocks in the circuit. For the other two blocks, we have much regular structure. The control block has somewhat relatively regular structure since it is made of finite state machines, and finite state machines have pretty regular structure. In the data path block, it has much less regular structure than the control block because in the data path, we have specific operations and combinatorial functions, so the interconnection between the different blocks is ad hoc for every particular function to be implemented. We can observe that in the last 30 to 40 years, the placement of the various building blocks on the silicon chip and the routing or design of interconnections is getting more and more automatic. Compared to the first digital circuits in the 70s, which were completely done by hand, the process nowadays is almost completely automatic. Typically, the designer will only check the automatic placement of the blocks and the interconnection. This is mainly because the use of increasing set of software tools help the designer increase its productivity in terms of transistor per month. It also affected the type of circuits in the sense that if we compare the images of the circuits as it evolves in time, we can see that the structure becomes more and more regular. As we are experiencing a transition to complete automation, one essential aspect that we have to consider is a trade-off between flexibility and efficiency. One way of improving productivity is to reuse large parts of the hardware, program it to perform other particular functions. From the point of view of flexibility, this is a major advantage and it also increases the speed of design. On the other hand, one disadvantage is that typically this reprogrammed hardware is less performing than a hardware fully designed for a particular application. The other aspect is that the more layers of software added to some hardware, the higher the power consumption. These are general considerations, and one has to know that any flexibility and programmability of the function has a cost in terms of performance and in terms of energy consumption. These trade-offs can happen at different degrees. We have here at the top of the scale hardware that are completely custom for the application. The hardware is done once and cannot be modified after manufacturing. It has no programmability at all, therefore this type of hardware gives you the best flexibility, but it gives you the highest energy efficiency. Then by going down this scale, we can increase the flexibility, but consequently reduce the energy efficiency. The next step in the scale is a configurable hardware. Basically, it is a hardware that has some parameters which can be changed by software. The trade-off continues as we go lower through the scale, application-specific processor, then embedded microprocessor, still adding more flexibility but getting less and less energy efficient. If we consider these types of solution, there is an additional essential aspect to consider related to the cost of the integrated circuit. The cost of an integrated circuit changes a lot depending on the type of solution. And if we want to consider the cost of the integrated circuit, we can split it into two components. We have the recurring expenses and the non-recurring expenses. Recurring expenses are the so-called variable costs, which simply means they are proportional to the sales volume, the expenses that you have for each additional chip that you make. Non-recurring expenses, also called fixed costs, are independent of the sales volume. Design is a fixed cost. The cost of manufacturing and fabrication of each chip is a variable cost. The cost of shipping the chip is a variable cost. The cost of fabricating the mask for the fabrication of the chip is a fixed cost because you do it once, then you could use the same set of masks for the whole production. Just to give you an example. Let us understand the possible implementation approaches that are available for a digital design. First is the custom design. Custom design essentially means transistor by transistor design of the complete circuit. Then we have the semi-custom design. Semi-custom design means we are using something that is pre-designed, and in the case of semi-design or semi-custom design, we have two options. One is to do a cell-based design. In cell-based design, some cells or particular blocks have already been designed, and we can just use them, but we still need a complete manufacturing run to fabricate the ICs. In the case of cell-based design, we typically have two options. One is the so-called standard cells, which means very simple basic cells have been already designed and are available to be placed. For example, simple logic gates. Another option for the cell-based design is a macro cell, which are larger cells, for example, a memory block, ready to be used and placed on silicon. Still considering semi-custom design, we have the option so-called array-based design. The main characteristics of an array-based design is that we do not need a complete manufacturing run. Some part of the manufacturing has been done. For example, we start on a half-done chip or a completely fabricated chip, and the only option we have available is to program it. One of the options is the gate array. In gate array, we only need to put the interconnections and eventually, possibly to program it. Then we have the reconfigurable logic such as FPGA or microprocessors, in which we start on a chip that is completely fabricated and the only option that we have is to program the hardware. These set of approaches can be ranked according to the most energy efficient and most flexible. And still, there is a trade-off, and the trend of the trade-off is indicated by the arrows. As we move to the left, the performance gets higher, while moving to the right gives higher flexibility. On the left side, we have higher non-recurring expenses because everything has to be done. For example, if we use custom design, not only we have to completely manufacture the chip, but we also have to design every single part of the chip. And as we move to the right side, we design less and less, and in those situations, we have less non-recurring costs because the masks have already been done, but the recurring costs gets higher. Let us examine in detail these approaches. We already know that with custom design, we have high performance and expense of low flexibility. Another obvious thing is that it is more time consuming. Sorry. And the fact and the fact that it is time consuming has actually two consequences. One is the high cost of design, which means we have high non-recurring expenses. Another typical issue is the high time to market. A complete custom design takes months to accomplish, even with a large team size, yet you only have a very small window of time in which your product is very competitive. Therefore, market opportunities can be a problem. You can lose the good timing and can enter the market in which your solution is not the only one available anymore, and so you reduce the price to sell it. There are few typical cases where a custom design is used. Custom design is always used for blocks that have to be used many times, such as standard cells or library cells. It is also used, or very high volume ICs are also custom designed. For example, some parts of microprocessors, especially those with very high volume ICs. You also do custom design when cost is not an issue. For example, in the case of military and supercomputing applications, cost is not an issue, and more importantly, they require high performance designs, thus they use custom designs for such. For the semi-custom design, like in the case of cell-based semi-custom design, we need a library of cells. Standard cells are blocks that are used millions or billions of times, such as logic gates with inputs, the so-called medium scale of integrated circuits, like decoders, encoders, multiplexers, that are used several times. You have a library of standard cells where you can select the cell, the type of logic gate, or circuit that you need and you put it in your design. The macrocells, as mentioned earlier, are used typically for memory banks. One particular or special case of macrocell is the megacell, which is typically a large macrocell such as microprocessor, DSP, and PCI interface. The question is, how do we use the standard cell and the macrocell? Here we have an image of a pretty old standard cell, a first generation of standard cell. Here, as you can see, cells are arranged in rows, and these rows of cells are designed to have the same height, but may vary in width depending on the complexity. The rows are separated by spaces, which are used as routing channels for interconnections between the different building blocks. The input-output connections are placed in the upper or lower side for convenience of using the routing channels for interconnections. And as what we can observe, this is an inefficient design because it is not very dense. There is a lot of space that is reserved and used for routing channels, and a lot of these spaces are unused. On the contrary, here is an image of a new generation standard cell. As you can see, we now have a more compact solution. There is no routing channels at all because the routing is done on top of the standard cells. What we are seeing here are the interconnect layers hiding the cell structures. Moreover, the route is not limited to the periphery of the cells, and rows are adjusted to one another. As a result, we now have a denser structure. This is also due to the fact that we can now have 11 layers of metal as compared to only 3 layers before. So how do we arrive at a standard cell implementation? Because of course, before you know exactly what are the blocks that you need, first you need to design the complete chip. The typical sequence that has to be done begins with a design at a high level of abstraction, typically using hardware description language. Once you have the hardware description language, you can now use some specific logic synthesis tools to translate this description language in terms of high-level language into a level design. A gate-level design is a design of logic circuit at the level of single gates. Here you can now use the standard cell approach to design the complete chip. Once you have a gate-level design, you now need to use the placement and routing tools in order to place all the standard cells corresponding to each gate you need onto the silicon die and also start to place the routing and interconnections between the gates. At least you need to reach this point, this level of this description in order to think in terms of standard cells, and this part can be almost automatic. The placement and routing tools, depending on the complexity of the chip, can already place all standard cells and put the routing, and one typically need to adjust the placement and routing for improvement. Then we can now have the standard cell layout, which can now be sent to the foundry to create the masks for fabrication. This type of process is very convenient for a fabless operation because you don't need to interact with the foundry, not until the end of the process. You only need to know the constraints that the fabrication process is giving you, which are described in terms of design rules. In the case of macrocells or macromodules, we have two types of macrocells. We have hard macrocell and the soft macrocell. In a hard macrocell, the performance is maximized for one macrocell only, and that macrocell can only be used with one specific CMOS fabrication technology. They are typically used for memory but is also used for embedded technologies. In soft macrocells, the gate netlist and implementation from gate netlist to standard cell is done depending on the specific CMOS technology used for the implementation. There is no predetermined physical implementation because it is easier to sell a macrocell that can be used to all CMOS processes than to optimize the same macrocell for every different foundry process. This is more convenient, but because of the usual trade-off between flexibility and efficiency, it has a lower performance. Let us have a look at the semi-custom design flow. Basically, it is identical to what we have described earlier, but with some more details and also with some illustrations of the iterations that we need to do. We can distinguish two main phases of the design flow. We have the functional implementation phase and the phase of physical implementation. At the level of the functional implementation, we need to make sure that the circuit works, and then in the physical implementation, you want to arrive at the physical layout of the chip in order to send everything to the foundry. For the first phase, we already mentioned the main 3 points, but it is interesting to see the loop that is required. First, we have the design capture stage, in which basically use VHDL to the hardware description language and the IP blocks that we want to use. After which we perform a logic synthesis using the necessary logic synthesis tools. At the end of which we have a list of all the gates, the so-called netlist, and then we have all the constraints in terms of placement and routing. We know the interconnections between the different gates, but also the logic synthesis stage gives us some constraints on the interconnections. For example, the length of the wire between different gates, the delay in the propagation of the signal between two logic gates is a function of the length of the interconnections, so we typically have constraints in terms of maximum length of the interconnections, and we have to observe this constraint when we place the two different state gates on the silicon die. At the end of this phase, we do a pre-layout simulation and verification. Before doing the layout, when we have only the gate netlist, we perform a simulation at the level of gate netlist in order to verify that the behavior is the same to the hardware description language based description of the circuit. We need to check that at the gate level, the circuit is behaving exactly as we want. If the control check says no, or probably if there is a problem, the phase should be repeated again until all the errors are addressed and cleared. Once error-free is achieved, we can now proceed to the physical implementation phase. We need to pass the netlist to the physical layout of the chip. The first stage in the physical layout phase is the floor planning, which means placing every gate in its particular position. The main purpose of the floor planning is to understand the total space that is required by the chip. The exact positions of the gates are less important. The second stage is the placement and routing, in which we decide the exact position of each gate, governed by the constraints that are given by this stage. This stage, as we mentioned earlier, is done quasi-automatically in the sense that there are some software tools that can do it, but typically we still need to perform adjustments. At the end of the placement and routing, we already have a physical layout. A physical layout of the circuit on the silicon, and then we need to check if this physical layout corresponds to the gate netlist that we have on the functional implementation phase. If so, then the layout is now ready for electrical circuit extraction. There are tools that perform an electrical circuit extraction, and from the layout, without knowing anything about the circuit, they extract an equivalent electrical circuit and then simulate the extracted electrical circuit and verify that it works as the gate netlist. Once verified and we can say that the physical layout is identical to the gate netlist, then the design can now be sent to the foundry. From this layout, the masks will be generated and the integrated circuits will be fabricated. But if upon simulation and verification the errors arise, we need to go back and repeat the physical implementation phase again until there are no errors that will appear. So this is the design flow for the cell-based semi-custom design. For the array-based implementation, it is different because we do not require a complete manufacturing run. Let us look at the two different options that we have. The first is the gate array. In this case, we have mask programmable arrays. As mentioned earlier, some parts of the fabrication are done and we only need to do the interconnections. So the diffusions of the various areas have been already done. We only need the metal lines. Typically, most of the common area logic in finite state machines can be performed with gate array. Gate arrays have lower non-recurring costs. The other option is the use of Field Programmable Gate Array or FPGA. In this case, we only need to program the hardware. There is a complete separation between the manufacturing phase and the implementation phase. The chips have already been fabricated. We just buy them and program them. On the positive side, we have short time to market and low non-recurring expenses, but on the negative side, we have performance loss and we have high recurring expenses. That is all about the implementation strategies for digital ICs. Thank you.